Hello everyone, myself Dr. Anurag. Today we are going to talk about chemical equilibrium. Let's talk to the various aspects of chemical equilibrium one by one. Chemical equilibrium can be defined as a particular state of a reversible reaction where the rate of forward reaction becomes equal to the rate of backward reaction. It is a dynamic process where the conversion of reactant to product and product to reactant continues, although there is no net change in number of reactant and product molecules. When we plot a graph between the reaction rate and time, you can see that initially reactant concentration is very high. As the time proceeds, it decreases because of the conversion into the product. Whereas in case of product, initial concentration is zero. As time proceeds, it increases, and there is a particular point where both the reactant concentration and product concentration matches. This is nothing but equilibrium point. So at equilibrium, we can say that the concentration of reactant and product remains constant, provided temperature remains constant. Okay, let's talk about effect of catalyst. Equilibrium point remain unchanged in presence of catalyst. You can see from this particular graph that when we have a particular reaction, the product is forming from the reactant with respect to time. Product concentration increases with respect to time. The reactant concentration decreases with respect to time, and there is a particular point where the equilibrium exists, where the rate of both forward and backward reaction become equal. When we add a catalyst here, the reaction rate changes and it becomes faster. However, the equilibrium point doesn't change. This is very important. It still remains unchanged in presence of catalyst. Now, what is the law of mass action? The law of mass action can be expressed as the rate at which a substance react is proportional to the product of active mass of that reactant. Let's say we have a particular substance A. Active mass can be represented in terms of square brackets, which is nothing but it represents molar concentration. Now let's talk about type of equilibrium. Equilibrium can be classified in two categories. One is physical equilibrium and another is chemical equilibrium. Physical equilibrium can be simply understood from certain examples such as solid-liquid equilibrium, liquid-gas equilibrium, gas-solution equilibrium, and so on. If we take a simple example of ice water as a solid-liquid equilibrium, we can find that at particular equilibrium position, the rate of melting of solid phase ice is equal to the rate of freezing of liquid water. Similarly, in case of water and vapor, if they exist in equilibrium, the liquid phase, that is water, the rate of evaporation become equal to rate of condensation of the vapor. In case of gas solution equilibrium, if the solute particle is a gas dissolved in a particular solution, they can exist in a particular equilibrium where the solubility of gas is directly proportional to pressure, which can be described by the Henry's law. Let's talk about law of chemical equilibrium. For a reversible reaction where reactant A and reactant B are converting into product M and product N, if there is a equilibrium between reactant A and B and M and N, then according to law of mass action, the rate of forward reaction can be written as uh, active mass of A and active mass of B is directly proportional to rate of forward reaction. There is a proportionality constant Kf, which is known as rate constant for the forward reaction. Similarly, for backward reaction, we can write rate of backward reaction Rb in terms of active mass of M and active mass of N. There is a proportionality constant Kb, which is nothing but rate constant for the backward reaction. Hence, at chemical equilibrium, we know that rate of forward reaction is equal to rate of backward reaction. We can substitute the equation which we have just got it. Just by rewriting this equation, uh, the K forward divided by K backward is nothing but equal to active mass of M and active mass of N divided by active mass of A and active mass of B, or in simply saying that the ratio of K forward and K backward at particular temperature is constant and known as equilibrium constant, which we can define as capital K, where this capital K is nothing but rate rate constant for the forward reaction and divided by rate constant for the backward reaction. If we are defining this equilibrium constant in terms of concentration, it is known as Kc, where the equilibrium constant Kc can be expressed as concentration of product M multiplied with concentration of product N divided by concentration of reactants A and B. We can substitute instead of writing in square bracket, we can write in terms of symbol C, which denote nothing but concentration. So as we said that if equilibrium constant is expressed in terms of concentration, it is known as Kc. Similarly, if we define our reactant A, B and product M and N are in gaseous state, the equilibrium constant can be expressed in terms of pressure, where the equilibrium constant is known as Kp. If we define it in terms of pressure, that the term concentration is replaced by the term pressure, the pressure of product M multiplied with pressure of product N divided by pressure of reactant A and B. In order to establish a relationship between Kp and Kc, we can take a simple example of a reversible reaction which we have discussed so far. Taking a reaction A over A and B, both are reacting and converting into the product M and N. We know the expression of equilibrium constant at equilibrium constant in terms of pressure Kp, which can be defined as pressure of M multiplied with pressure of product N divided by pressure of reactant A and B. From ideal gas equation, we can write that PV equals to nRT, where rewriting this equation, pressure is nothing but equal to N by V RT, where this N by V is nothing but concentration. So we can simply rewrite this equation of pressure as CRT, where C is the concentration. Just by replacing the term pressure in the expression of Kp, where we know that pressure Pm is nothing but Cm, concentration of product M, multiplied with RT to the power M. M is number of moles of product M. Similarly, pressure of product N can be replaced with concentration of N multiplied with RT divided by concentration of reactant A multiplied with RT to the power. And similarly, we can replace the term pressure term PP with CPRT. Here, we can take the concentration term separately, and we can rewrite this equation where the term RT in terms of M plus N minus A plus B, where M plus N is nothing but number of moles of product and A plus B is nothing but number of moles of reactant, which can simply rewrite with respect to expression delta N. So Kp is nothing but Kc multiplied with RT to the power delta N, where delta N is uh, the difference between number of moles of product and reactant. Units of Kp and Kc. We know that Kp is expressed in terms of partial pressure of products and reactants. So the unit of Kp is nothing but atmosphere to the power delta N, where delta N corresponds to difference between number of moles of product and reactants. Similarly, if we express Kc, which is written in terms of concentration, which has a unit of mole per liter, the unit of Kc can be expressed then in terms of mole per liter to the power delta N, where delta N is again number of moles of product minus number of moles of reactant. When delta N is 0, then the Kp and Kc are specified only by numbers. However, the units of Kp and Kc are omitted in conventional writing. Now let's talk about the characteristics of equilibrium constant. The first thing is that it depends on temperature. It does not get affected by addition of catalyst. The next thing which is very important for us is if reaction is reversed, then the value of equilibrium constant is also inverted. For example, if we take PCl5 is converting into PCl3 plus Cl2, the reaction equilibrium constant is K. If we reverse the reaction where the product is now become reactant and we try to calculate what will be the equilibrium constant, then the new equilibrium constant K dash is nothing but equal to 1 by K. Similarly, if we divide a reaction by N, then equilibrium constant is nth root of the original. Here N is the number of moles. Let's say initially we have taken PCl5 as a 1 mole, then it's converting into PCl3 and Cl2, and we are getting a equilibrium constant K. Now if we divide all the number of moles by 1 by N for the PCl5, similarly for PCl3 and for Cl2, then the equilibrium constant comes equals to K root over N. As we are dividing by N, similarly we can also multiply with N number of moles by reaction, and we get a nth power of the original to the new equilibrium constant. For example, we have a PCl5 reaction which is converting into PCl3 plus Cl2. Now we are multiplying it with respect to n number of moles, then n PCl3 and n Cl2. The new equilibrium constant K dash, it will be a K to the power n. For example, we take n equals to 2. We are multiplying with 2 number of moles, then 2 PCl5 is converting into 2 PCl3 plus 2 Cl2. then the new equilibrium constant is nothing but K square. If reaction takes place in more than one step, then the equilibrium constant is product of equilibrium constant in each step. For example, if we have a reaction where reactant A is converting into the product D and the reaction is showing in equilibrium, then that the equilibrium constant K equilibrium is nothing but the equilibrium constant which we are getting from each step A to B, B to C or C to D, or maybe n number of steps involved in between them. Then the corresponding equilibrium constant, if we take multiple of that, K1 into K2 and K3, that gives us the total equilibrium constant. Okay, let's talk about the reaction quotient Q. It is nothing but for a particular reaction when we take product concentration divided by reactant concentration other than equilibrium stage, the expression is known as Q. If Q equals to K, then equilibrium exists. If Q is greater than K, then more backward reaction takes place. If Q is less than K, then more forward reaction takes place. So the relationship between Q and K can tell that whether reaction will proceed in forward direction or backward direction. Okay, let's talk about chemical equilibrium in terms of free energy change. It is very important to know how the free energy is changing for a particular reaction. Free energy change delta G is expressed as the free energy of the products minus free energy of the reactants. The free energy per mole of any component is called the chemical potential. Hence, we can write delta G is nothing but m number of moles multiplied with chemical potential of product M plus n number of moles multiplied with chemical potential of product N minus chemical potential of reactant A and chemical potential of reactant B respectively. For a spontaneous reaction, we know that delta G has to be negative. Hence, the summation of free energy of product should be always less than summation of free energy of reactant. As we know that in the beginning, when we have the reactant only in the reaction vessel, the reaction has to proceed and it has to be delta G has to be negative. And the free energy is associated with this particular reactant is only contributing in terms of free energy change for the particular reaction. So initially, where delta G product is 0, delta G is coming only from the reactant part. So that is already negative. As the reaction proceeds, let's say from here to here, when product formation takes place, as a result, the free energy of reactants keep on decreasing, which is initially, let's say it was here, then it is keep on decreasing because the addition of product. As a result, free energy of reactant keep on decreasing, and at particular point, we find that the summation of product and summation of reactant free energy becomes equal. This is a particular point where delta Z becomes 0 and it is known as equilibrium point. At Q at delta Z equals to 0, we know that at equilibrium point K become equals to Q. So as we have discussed earlier, when K is greater than Q, more forward reaction takes place. When K is less than Q, it try to go to the backward direction. Let's do now the thermodynamic derivation of law of chemical equilibrium. If we take a simple example of a reaction where A and B two reactants are converting into the product M and N, at equilibrium at constant temperature and constant pressure, the free energy change delta G becomes 0, which is nothing but the difference of free energy for this product and reactant. We know that we can express the free energy in terms of chemical potential mu m and mu n for product M and N respectively. Similarly, free energy for reactant A as mu A and reactant B as mu B. If we simplify this equation further, since it is equal to 0, the product chemical potential or the summation of free energy of product becomes equal to summation of free energy of reactants. If all reactant and products are ideal gas, the chemical potential of any component is given by mu equals to mu naught plus RT ln P, where P is the partial pressure of the gas in the given reaction mixture, and mu naught is nothing but chemical potential in standard state. So we can write the equation of chemical potential for the each of the species A, B, M, and N. Substituting these equation in original equation which we got initially, we get the substitution, and when we expand it, just multiply the number of moles of each M and N for the product A and B. When we rewrite this equation in terms of standard state of chemical potential of product and standard state of reactants, we get this particular expression. We know that when we have number of moles multiplied with natural log of partial pressure m, we can rewrite it in terms of natural log of partial pressure P to the power m. Just substituting this or rewriting in this previous equation and taking RT as common, we get this particular expression where the right hand side, the summation of chemical potential for the reactants can be designated as mu A and mu B equals to summation of free energy of reactant, and for the chemical potential of mu M and mu N naught, this is nothing but standard state free energy for the products. Just by rearranging this equation, we get this equation. We are simplifying it further, taking this RT to the denominator to the right hand side. So this is the equation which we got last slide. Natural log of partial pressure of product and partial pressure of reactant ratio is equal to negative of summation of free energy change in standard state of product minus free energy in the standard state for the reactant divided by RT. We can write the numerator is simply by free energy change in standard state delta G naught. We know that the left hand side term is nothing but the ratio of partial pressure of product divided by partial pressure of reactant is Kp. So the expression can be written as natural log of Kp equals to minus free energy change of the reaction in standard state divided by RT. Or we can write the free energy change in standard state is equal to minus RT ln of Kp. Similarly, if molar concentrations are taken into consideration, the expression as mu equals to mu naught plus RT ln C, and the subsequent derivation leads to the equilibrium, where the equilibrium constant Kc can be expressed in terms of product concentration divided by reactant concentration. And finally, we get an expression that delta G naught free energy change in standard state is equal to negative of R multiplied by temperature T into natural log of Kc. Here the important thing is that if we get free energy change in the standard state delta Z naught from Kp and Kc, they are always different except when delta N equals to 0, in that case Kp becomes equal to Kc. Now let's talk about the Van Hoff reaction isotherm. For any state other than standard state at constant temperature and pressure, the chemical potential mu can be expressed as chemical potential in standard state plus uh, gas constant R multiplied with temperature T and natural log of uh, pressure P. Especially when activity coefficient is taken A, activity coefficient gamma E is equal to 1, where the activity is almost equal to the pressure. For such free energy change, the delta G can be expressed as summation of product minus reactants, and we get the expression which we talked about earlier as well, where product chemical potential and reactant chemical potential difference gives us the free energy change. Further expanding the relationship, we get on rearrangement by keeping the chemical potential term in standard state aside and keeping RT as common. We get the expression such that delta G equals to uh, number of moles of product N multiplied with chemical potential of N plus number of moles of product N multiplied with chemical potential of product N minus chemical potential of reactant A and chemical potential of reactant B plus RT natural log of partial pressure of product divided by partial pressure of reactants. Uh, Here we can write this particular term equals to free energy change of the product, and the second term is equal to the free energy change for the reactant, which is nothing but uh, total free energy change in the standard state, whereas the other term RT partial pressure of product upon partial pressure of reactant is nothing but QP, since it is not an equilibrium state. And we can simplify this equation and we get the final expression as delta G equals to free energy change in standard state plus RT multiplied with reaction quotient QP. This equation put forward by J.H. Van Hoff and known as Van Hoff reaction isotherm. It provides free energy change in terms of standard free energy, and the factor depends upon the partial pressure of the reaction mixture, that is nothing but pressure quotient. For a reversible reaction, we know that at equilibrium delta G is equal to 0, so QP become equals to KP, and the below expression terms as return can be written as delta G equals to 0, that is equal to delta G in the standard state plus RT ln Kp. So we get the expression for delta G naught equals to minus RT ln Kp that we derived earlier as well. By substituting this term in the Van Hoff equation, we can rewrite the Van Hoff equation in terms of delta G naught equals to minus RT natural log of Kp plus RT natural log of pressure quotient. Now let's talk about one-half reaction isotope. The expression for variation of equilibrium constant for a reaction with temperature put forward by Van 't Hoff and called Van 't Hoff equation. It can be derived as follows. We know that delta G naught equals to minus RT ln Kp. Now differentiating this equation with respect to temperature at constant pressure, we get the expression such that uh, the derivative of uh, delta G naught free energy in the standard state with respect to temperature at constant pressure P is equal to, now since we are differentiating, we have R which is a constant, we have two factors, two variables here, temperature and uh, Kp, equilibrium constant Kp. So now taking the differential equation with respect, differentiation with respect to temperature, we get the expression minus R natural log of Kp minus RT the natural log of Kp divided by dt. Now multiplying this equation throughout by temperature T, we get this equation in terms of particular expression in the middle that is equal to delta G naught. Now rewriting this equation, we get an equation that T multiplied with the derivative of free energy in standard state uh, with respect to temperature at constant pressure P is equal to the free energy in standard state minus RT square uh, derivative of natural log of Kp with respect to temperature dt. Now, according to Gibbs-Helmholtz equation, we know that delta G can be expressed in terms of delta H plus T derivative of free energy with respect to temperature at constant pressure P. Just by substituting this in a standard state, we get this expression and rewriting it as we have written the equation 1, we get this particular expression. Just by comparing equation 1 and 2, we can easily write that this particular term delta G naught minus delta H naught, where we can easily get the expression for delta H naught enthalpy change in the standard state, that is equal to RT square d natural log derivative of natural log of Kp divided by with respect to temperature. And finally, we can rewrite this equation with respect to derivative of natural log of Kp uh, with temperature is equal to enthalpy change in the in the standard state divided by gas constant R multiplied with T square. This particular equation is called Van 't Hoff equation. The integrated form of this equation can be expressed as we just take the uh, dt to the right hand side. So by taking integration of the previous equation with respect to the limits of Kp and Kp such as Kp1 and Kp2 uh, and ranging the temperature from T1 to T2, the integration gives us equation that natural log of Kp2 divided by Kp1 is equal to negative of standard enthalpy change divided by gas constant R minus 1 by T2 minus 1 upon T1. We can rewrite this equation, we can multiply this negative sign here, we can take it inside, and we get the expression in the right hand side as delta H naught, free enthalpy change in the standard state divided by gas constant R minus into 1 upon T1 minus 1 upon T2. If we express the enthalpy change without standard state, we can rewrite this equation as log of Kp2 upon Kp1 is equal to uh, enthalpy change divided by 2.303 into gas constant R multiplied with 1 upon T1 minus 1 upon T2. Let's take an example of this one. The equilibrium constant Kp for a particular reaction is given at 300 K and 340 K, and we have to find out what will be the enthalpy change uh, in the given temperature range, and if we have to calculate the entropy change as well for this particular reaction. How to solve this question? This is the data which has been given, Kp1 and Kp2. What are the T1 and T2? The temperature range. We know what is the gas constant R, 8.314 joule per Kelvin per mole. From want of equation, if we apply, we can simply substitute the data given and we can find out what is the corresponding delta H from here. Let's do this exercise. We get the enthalpy change for the reaction that is coming as 48.825 kilojoule per mole. Further, if we have to find out what is the entropy change, we know that delta G is equal to delta H minus T delta S. At equilibrium, delta G is equal to 0, so delta H become equals to T delta S. So delta S is equal to delta H upon T1. So at temperature T1, we can get what is the entropy change. Similarly, at temperature T2, we can get entropy change. And we can simply put the values and we can get the answer. Now let's talk about Le Chatelier's principle. If a system is in equilibrium is subjected to change of concentration, temperature and pressure, the equilibrium shift in a direction that tends to undo the effect of change imposed. Let's talk about them one by one. Take the first case, the effect of concentration. If we take a simple example of a reaction where the A and B two reactants are converting into the product C and D respectively, the equilibrium constant Kc can be represented as product concentration divided by reactant concentration. If we add more reactant, equilibrium is disturbed and it will try to get back to the equilibrium. In order to do that, more product formation has to take place, and that's why more forward reaction will happen. Similarly, on addition of product, let's say C or D, or if we increase the concentration of product C and D, again the equilibrium is getting disturbed. In order to attain the equilibrium back, more backward reaction has to take place so that more reactant can be produced. Similarly, if we try to remove any product, or we can say that if we are removing product concentration, if we are decreasing the product concentration, in that case also more forward reaction takes place in order to have the equilibrium exist. Similarly, if we remove the reactant, more backward reaction takes place. Let's take an example of this one. We have a Haber process where ammonia is produced. If we liquefy the ammonia side by side, that means there is a decrease in product concentration because product is ammonia gas. It leads to more forward reaction. Let's take another example, the manufacturing of calcium oxide. The gaseous CO2 is allowed to escape. Since it is a product, if we are removing the product CO2, more forward reaction takes place. Let's take a quiz here. If we have a simple reaction where carbon dioxide is reacting with water and converting into HCO3 minus and H plus. On removal of carbon dioxide gas, what will be the effect on medium pH? Whether it will increase or decrease? Think and answer. Now let's talk about the second variable, that is temperature. If we have an exothermic reaction, it is always favored by low temperature. Whereas if we have endothermic reaction, it is always favored by high temperature. If forward reaction is exothermic, then backward reaction is obviously endothermic also. We know that for exothermic reaction, delta H is negative. Hence, if we increase the temperature, more backward reaction takes place. Equilibrium shift towards the reactant. If we have endothermic reaction, then we know that delta H is positive. In that case, if we increase the temperature, more forward reaction takes place. Equilibrium shifts towards the product. It can be explained using one-half equation, where we know that the derivative of natural log of Kp with the temperature is equal to enthalpy change divided by RT square. If delta H is positive, that is endothermic reaction, it is greater than 0, then this particular derivative component, it is positive, which means if we increase the temperature, Kp has to increase. If increase of Kp takes place, then more forward reaction takes place. Similarly, if we have delta H, enthalpy change in standard state, negative, that is less than 0, this derivative component, it becomes equal to negative, and hence if we increase the temperature, Kp will decrease. If the decrease of Kp takes place, it implies more backward reaction. Now let's talk about effect of pressure, how the pressure variable make changes in terms of equilibrium constant. If we have number of moles of product is equal to number of moles of reactant, then there is no effect of pressure. If we have delta N is positive, that means number of moles of products are more. The low pressure favors these reactions. That means if we increase the pressure, more backward reaction takes place. Hence, we should decrease pressure for these reactions. In another case where delta N is equal to negative, that means number of moles of reactants are higher. In that case, high pressure favor these reactions. If we increase the pressure, more forward reaction takes place. Let's take an example of ammonia formation where N2 and 3 hydrogen molecules are reacting to convert into ammonia. We know that delta N is negative. Here, high pressure leads to more yield of ammonia. So this is the one factor where if we increase the pressure in case of Haber process, we can get more number of ammonia molecules. The fourth thing is the increasing the pressure in equilibrium tends to shift in direction where volume decreases. Let's take a certain example of this. Where we have a ice and water into the equilibrium, we know that ice has more volume compared to less volume. If we increase the pressure, ice converts into water. That means melting of ice takes place. Similarly, if we take another example that water is in equilibrium with vapor phase, that means water is having less volume and vapor is having more volume. So on an increase in pressure, the equilibrium tries to shift towards from vapor to water, or condensation of water take place. Now let's talk about the effect of insertion of an inert gas. Apart from pressure, concentration and temperature, if we insert an inert gas, that means we are changing the volume. And how that is going to affect? It is simply make an effect towards opposite direction as expected due to pressure. If we have delta N equals to 0, it will not lead to any effect in the reaction. However, if we have delta N equals to positive, more forward reaction takes place. Whereas in case of delta N equals to negative, more backward reaction takes place. This is all about Le Chatelier's principle and certain characteristics we have seen. Thank you for listening. Let's do more practice on it.